Hey everyone, this is Dr. Walker. This is video 35C called Non-Uniform Circular Motion. In the previous videos, we've been talking about uniform circular motion, where an object moves in a circle at a constant speed. But we know that it's totally possible to move in a circle and our speed changing. When that happens, we have non-uniform circular motion. Imagine that you're driving in a car over here at point A and you have a certain velocity. The velocity is always tangential to the circular motion. Imagine that once you reach point B, you have sped up. So your velocity has changed. Well, that is non-uniform circular motion. So the difference with this type of motion and the uniform circular motion is simply that we have a tangential component to our acceleration, an acceleration component in the same direction as the velocity. If we wanted to find that component, it would just be the regular dv dt to find that tangential acceleration. We also have a radial component to the acceleration. It's called a sub r here. It's the same thing as the centripetal acceleration. The magnitude of it is v squared over r. So let's say that at point B, we are trying to find the total acceleration of our object. Well, it's going to be the vector sum of the centripetal and tangential accelerations. So we can write the equation as the acceleration is going to equal to the tangential component plus the radial component. And we know that to do this kind of vector sum, since the tangential and radial components are perpendicular to each other, we know that this vector sum is just going to use the Pythagorean theorem to find the magnitude of that total acceleration. We'll do an example shortly. We can also find the total force of our object the same way. The total force is going to equal to the net force tangential component plus the net force radial component. So we're just trying to show that yes, it is possible to move in a circle and not have a constant speed. It's just going to change the net acceleration a little bit. Let's look at this question. As the car moves from point 1 to point 2, its speed doubles. What is the direction of the car's average acceleration between these 2 points? So we're moving in a circle, our speed is changing, so that's non-uniform circular motion. We're looking for average acceleration, though. We haven't talked about that recently. We just talked about the tangential acceleration and the radial, but not the average. So this question actually does not use the equation that we just saw. We'll see that in a future example coming up very soon. This question uses the definition of average acceleration that we talked about a long time ago, right? That acceleration is a change in velocity per time. So always pay attention to what the question is asking. Take a second and think about, can you figure out the direction? Keep in mind that the direction of the average acceleration, which we also write with just a line over it, I prefer that way. The direction of the average acceleration is in the same as the direction of the change in velocity. So if you can find the direction of the change in velocity, then you have your answer. So let's take a look. At point 1 here, we are going upward. We know velocity is tangential to that motion. So we can call that v initial. And then at point 2, we are moving to the left, but we have twice the speed. So our vector is about twice as long, going straight to the left. We'll call that v final. So what is the direction of the average acceleration? We need to find a change in velocity. Remember that delta v means v final minus v initial. Do you remember how to subtract vectors? To subtract vectors, you want to add the negative vector. So we want to draw our negative vi going down. Remember, a negative vector points in the opposite direction. And now we can do vf plus negative vi, right? We can write vf plus a negative vi, and we can add these vectors tip to tail. Let's go ahead and do that. we're going to have VF, and then we're going to add the negative VI. And we know that our resultant, which is the delta V, points from where we started to where we ended. So that must be the direction of the average acceleration, which is closest to letter F. Now keep in mind that if we just wanted to find the direction of the total acceleration, which this question did not ask, but let's just take a look at that real quick. For example, over here, typically our centripetal acceleration is always towards the center, and then we would have a tangential acceleration pointing this way. And so it would mean at this point, for instance, that our total acceleration would point this way. Not necessarily to scale here, but it would point in this direction rather than straight down. For the following videos, we will look at some examples.